All right, in this video we're going to go through a demo of modeling logistic population growth using InsightMaker. And we're going to start with a blank workspace here. I'm going to add a stock and call it population. And there we go. And we'll add a flow in and a flow out. Here, I'm going to change that to a flow in and make that a flow out. And let's see if I can make that straight. And make this one straight, and not that it matters, but let's call this one births and this deaths, and we'll add some vital rates. We'll add two variables, and we'll call those, in fact, let me just add them down here, and we'll call this one little b for the per capita birth rate, and this one little d for the per capita death rate, and just link those up. And now we'll just hit the equation editor and make sure that the total births is defined by the population times the per capita rate, and the deaths the same way, population times per capita rate. We'll start the population off at 50, and we'll start the birth rate off at 0.8 and the death rate off at 0.3. And let's just make sure that we see exponential growth. There we go. I'll configure it so I don't see the per capita rates in here and I just see the abundance. So we have our basic exponential growth model. Now let's implement density dependence. So what we're going to do is I'm going to add some variables, and add 4 variables to be specific. And a couple of them are going to define the density dependence relationship for the birth rate. That is how birth rate's going to decrease with higher density. And I'm going to add a couple of variables to represent how death rate's going to increase with density. So both vital rates are going to get less and less favorable as density gets higher, or population size gets higher. And it's going to make some links here. So those two are going to represent birth rate. These are going to represent death rate. And one of them I will call max birth rate. So I didn't type that in the right spot. It should be in the name category. That's going to be the maximum birth rate. And this one's going to be the maximum, or the minimum, minimum death rate, the most favorable death rate. And this is going to be density dependence for B. That's kind of the slope of the relationship. As density goes up, birth rate goes down. And I'll call this density dependence for the death rate. All right. Now, let's fill in the equations here. So this is density dependence, right? So both B and D, the per capita rates, are going to be dependent on the population size or density. There we go. So we can kind of represent this density dependence directly in this model using these links. And let's type in the equations. So instead of having a constant, now as density goes up, this per capita birth rate is going to go down. So I'm going to take the maximum birth rate minus this slope term times the population size. All right, so when the population size is really small, the birth rate's going to be really high, and as population size gets bigger, this birth rate is going to go down. All right, so density dependence there, and the same thing here. I want to take the minimum death rate and then add this density dependence relationship. So as population size goes up, death rate will go up as well. All right. So that's my density dependence relationships. Now I just have to put some numbers on these variables here. So the maximum birth rate, I'm going to leave the maximum birth rate as 0.8, and the death rate, just like I had before, was 0.3. All right, but now I have these density dependence terms. So the density dependence on birth, I will just use 0.0001 as the slope. And for the slope on the death rate, I will use 0.0005. Now, don't worry about these numbers. It just matters that, they define the slope of the relationship between birth and density and death rate and density. All right, so I think we've basically got this model correctly specified. So let's look at what happens. All right, and first of all, we can see we have this S-shaped curve representing logistic population growth, and I'm just going to get rid of all these constants here. So I just see population size over time, and it looks good. It looks like we have correctly specified a density-dependent population growth, and you can kind of see where carrying capacity is here. Carrying capacity is around 830 approximately. So that's kind of cool. We can see how we didn't even put a carrying capacity in this, but as if you read the Gatelli book, you'll see that you can actually compute carrying capacity. You can figure out carrying capacity just by knowing these values, of knowing the density dependent relationships and the minimum and maximum birth and death rate. At this point, just take a minute to answer the top hat questions related to this model, and we will go through one more way of representing logistic population growth in InsightMaker after this, and then now this model that we've just built here is one way to represent density-dependent logistic population growth. But there is actually a simpler way that we'll go through in lab as well. So I wanted to introduce that before we end this lecture or this demo here. So this models density-dependent specifically in the per capita birth rate and the per capita death rate. And this is a perfectly legitimate, good way to do it. But there is another way to do it that just uses R, the intrinsic rate of growth, and modifies R based on density. So instead of treating birth and death separately, you treat R, which is just basically the difference between births and deaths, or the net percentage population growth or decline each year, instead of representing both B and D separately. So let's build that model. And I just want to point out that model, the model that we're just about to build, really replicates this equation of logistic population growth. So unlike the model we just built here, where we don't have carrying capacity, we don't have R. Like this, it's not as clear how this represents the model we saw in lecture. This model here, this equation, whereas the model we're just about to build in InsightMaker does represent every element of this. So you'll see there's an R variable and there's a carrying capacity variable. So we're basically replicating this equation exactly. So let's get back to the Insight, and what I'm going to do is just get rid of this model and let's build a simpler model. So this time I'm going to create a stock and I'll call it N. All right. And the change in N is just a single, I think I have a link here instead of I need a flow. I want to flow in, all right, a single flow. And we have a single parameter. And that parameter is, actually we have two parameters. One is R, or the maximum rate of growth. I can call it R max. And we have one more parameter I should mention, and that is carrying capacity. I'll just call it K as we represent it in the equation. All right, so in this model now we can link our max to determine the flow and K. And when the abundance is well below carrying capacity, the population will be growing at around R max, and then the population will start to decline in growth as it reaches carrying capacity. So all we have to do here, and this is a super simple model, all we really have to do here is click on the equation editor and implement the equation. And so we have R max times n, right, which is the basic exponential growth equation. And then we have this extra term that represents the degree to which carrying capacity is empty, essentially. So 1 minus n over k. All right. So basically that's the equation. And in order to make sure that this flow could be negative if the population was declining, we can uncheck that box essentially. So that allows this flow to be negative or positive, and which is realistic, because what if the R is less than 0? Then we should be able to see negative growth, that is a flow out. So this flow can now be a flow in or a flow out. All right. And one thing just to notice is that when you do have these double-sided arrows, you'll see that now this flow has 2 arrows, meaning it's both an inflow and an outflow. You should see this white little dot in this arrowhead. That is you should see that on the arrowhead facing out from the stalk. That way, positive numbers of the flow represent inflows and negative numbers represent outflows. All right. So you have positive flows in this positive flows, or positive numbers represent positive flows. If this was reversed, then it gets really strange. And this is just a weird thing about InsightMaker, but it's something you should just keep aware of, because now positive flows will be flows out in this case, and negative flows will be flows in. And we don't want that, because that doesn't really make sense. So we always want to make sure that that little white dot is facing out, and that makes the equation and the model make more sense. So let's put some numbers on this. So let me just start this. This could be anything, and I'll just start it at 10, and let's make carrying capacity of 500, and I'll put an Rmax of 0.9. I'm just making some numbers up. I think in the lecture page, the website, it specifies some different numbers, so just make sure you use those numbers if you want to follow that model directly. And we have the equation already written there in our initial population. So I think we should be able to run this model. And it looks good. So, like normal, we might want to just take away these constants so we don't have to see them. Although, maybe you want to visualize carrying capacity on this model as well. And you can see that the abundance does equilibrate at carrying capacity eventually. You see this nice S-shaped growth curve. And if you wanted to, you could put value slider on the R term and the K term and just sort of see how this model behaves in different conditions. And let's put a different maximum. I'll put that maybe maximum of 1.5. And the K, I could put a value slider on that. And, we could go from 0 to 1,000 with a slider step of 1. And now we can just sort of play around with the model in different ways. Here we go. And I could make this model run faster if I wanted to. And there we go. And just start playing around. What if and maybe I want to move the settings up to a 100-year time frame. There we go. Now the population doesn't even get to carrying capacity in 100 years because my Rmax is fairly low. If I made the Rmax higher, I should be able to see the population now just quickly kind of jumps up to carrying capacity. So there's a lot to play around with here, but just wanted to point out that this is another way to represent the logistic growth model. We'll do more with this in lab. And with that, I will see you in the next lecture.